For our final project, our group decided to create a playground assembly in SOLIDWORKS. We chose this because we wanted something that had a lot of different parts and mechanical components instead of just a simple design. We felt the playground would be a good choice because it includes structure, supports, and interactive systems all in one project, which allowed us to practice many of the skills we learned throughout the course. Another reason we chose this project is because it worked really well for our group assessment. Since a playground has many separate components, it made it easier to divide the work equally between all group members, which helped keep the project organized and made sure everyone had an important role in the design process. We also thought this project would be visually interesting. A playground is something everyone recognizes, and different structures and components make the final assembly more detailed and engaging to look at. To make the project more advanced, we added extra components like a swing and a seesaw. The seesaw especially added realistic mechanical motion to the project and made the assembly more complicated in a good way because we had to think about how the part would actually connect and move together. It also allowed us to make different SolidWorks tools. Throughout the process, we used tools like sketching, extrusions, and cuts, and many more. Since the project included both simple and detailed parts, it gave us a chance to practice both basic and more advanced SolidWorks features that we have been taught throughout the semester.
I'm going to be talking a bit about the history of the model, but to quickly recap on what Maddie said about our inspiration for the model, it was from 3D CAD browser, and it is seen on the right. We chose this model because there were many parts for members to model, at least 2 to 3 per person, and we added on a seesaw and a swing for additionally complicated components and mechanisms. This model also allowed us to use various tools that we learned in class. So about the history of our model, as you can see, it's a playground. Playgrounds originated in the 1850s in Germany, and they were originally just sandboxes. But since then, there have been many safety procedures put into place in order to ensure the safety of the users of the playgrounds. So there are walls, there are railings, and there are additionally material and height constraints for real playgrounds in order to ensure the safety of the kids who are using it.
During this project, I was responsible for designing the most technically complex feature in the entire assembly. The platform of the playground required an advanced combination of SolidWorks tools, and building it pushed my modeling skills to a new level. In total, the feature incorporated 18 boss extrusions, each one carefully dimensioned to create the structural thickness and geometry needed for stability. To support these extrusions, I created 19 different reference planes, allowing me to control angles, offsets, and alignment with precision that wouldn't have been possible using the default planes alone. To shape the railing and post elements of the platform, I used 10 sweep features. These sweeps, along with the fillet tool, were essential for forming the rounded edges and connecting surfaces that give the playground its finished, professional appearance. Additionally, I incorporated 7 cut extrusions, which allowed me to remove material strategically for openings, slots, and safety-related clearances. Beyond the platform, I designed the roof structure using the loft feature to blend multiple profiles into a single continuous form. This gave the roof a clean, aerodynamic shape that complements the rest of the playground's design. When I moved into the assembly stage, I evaluated the model from a functional and safety perspective. As I examined the structure, I realized that certain areas of the playground appeared exposed and could pose a risk to users. Because of this, I made the decision to design an additional wall and barrier system, again using boss extrusions and cut features, to create a protective boundary. This addition not only improved the overall safety of the playground, but also enhanced the visual completeness of the final assembly. The platform serves as a central access point within the playground, designed to allow children to climb up and reach the surrounding amenities such as the slides, the tunnel, and the monkey bars created by my groupmates. Because it functions as the main transition area between multiple play features, its dimensions had to be extremely precise. Achieving this accuracy required several iterations of the model. Each trial involved adjusting heights, clearances, and connection points until the geometry aligned perfectly with the rest of the assembly. Ensuring that the platform was exactly the right size was essential not only for functionality, but also for maintaining proper alignment with the attached components. Above the structure, the roof plays an important visual and structural role. As the tallest element in the playground, it acts as a unifying feature that ties the entire design together. Its elevated position gives the playground a clear focal point, and its shape reflects the style commonly seen in real-world playgrounds. By incorporating this roof, the model gains both realism and architectural coherence, helping the entire assembly feel complete and intentionally designed.
So I worked on the slides. For the first slide, I basically used a U-shaped cross-section. I only needed a U for this one just because this is a one-person slide. I then was able to use spline to create multiple bumps, and this is the larger of the two. It's actually slightly taller, but it's the same width. The biggest challenge for the first slide was that the initial sketch would not register as one structure to sweep. So it kept saying there was some type of gap. And so I kind of just had to go in, fix all the dimensions, and yeah. For the second slide, it's W-shaped cross-section, because it's a two-person slide, similar procedure to make it. I used spline for the path. And the biggest challenge for this was I actually did it first, so the actual, general procedure needed to be developed. So originally I didn't even really know how to approach making a slide, but I was able to work through it. And for the features I used for both of these slides, I used the sketch for the cross sections, and then I mirrored it so it's even on both sides. And then I would use spline to construct the path of the slide, and a sweep to make a shell of the slide guided by the spline. So the steps to make it, just quickly recapping everything I've said, I sketched the cross section, mirrored over the y-axis, spline for slide path, and then just the general sweep for the slide structure. And that's how I constructed both of the slides.
For my contribution to the project, I designed and modeled two main playground components in SolidWorks, a climbing wall and monkey bars. For the climbing wall, I focused on creating a realistic structural design that would function as part of a playground system. I built the mainframe using extruded features and used cut features to shape details of the structure, such as the cutouts on the wall used to climb on. I also applied fillets to smooth edges and make the geometry more realistic, and used patterns where needed to keep spacing consistent for the climbing holes. For the monkey bars, I designed a structure made up of 4 poles and 2 side supports connected by evenly spaced horizontal bars. I used extrusions to create the main shapes, and again used patterning and sketch tools to maintain the equal spacing and symmetry between the horizontal bars. Fillets were also used to refine edges and improve realism. The goal was to make sure the structure was both accurate and visually consistent with real playground equipment. Overall, both parts were designed with proper scale, structural balance, and SolidWorks features to ensure they would integrate smoothly into the fully assembled playground.
For my part of the project, I made a swing stand and the swing seat. I chose these parts because they're an important part of the playground, and they also help me practice building both fixed and connected parts in SolidWorks. I first worked on the swing stand. This is the main frame that holds the swing up. It has 2 side supports and the top bar that connects them. While designing it, I had to make sure all the pieces were lined up correctly so the structure would be strong and fit properly with the rest of the playground. I had to also think about the spacing so the swing could hang in the right position. To build the stand, I started with the simple sketches to draw the basic shapes and measurements. After that, I used extruded base to extrude those sketches into 3D solid parts. This helped me create the main frame step by step. I also used extruded cut to make the holes and remove material where the swing would connect. These tools made it easier to build the structure and clear in an organized way. After finishing the stand, I moved on to the swing seat. This is the part where someone would be able to sit. I made it simple but mostly realistic in a size so it would match the stand. I ended up using sketching and extrusion again to build the shape.
Okay, so for my part of the project, I started by creating a sketch on the front plane using a circle to make the main shape of the tunnel. Then I used the extruded boss/base feature to extend the sketch into a cylindrical body. After that, I used the extruded cut feature to hollow out the inside of the cylinder and give the tunnel a realistic thickness of the wall. Next, I created the rectangular side plates on each end by sketching rectangles and then extruding them outward. Then I added the circular holes along the side of the tunnel using the extruded cut feature and then spaced them out evenly for symmetry. Then I applied fillets to the edges to smooth out the sharp corners and improve the overall appearance. Throughout the design process, I used dimensions and constraints to keep the model fully defined and proportional. To make the seesaw, I first started by designing the base and the triangular support structure using 2D sketches and the extruded boss/base feature. These supports act as the foundation and then they hold the main beam in place. After that, I created the main seesaw beam by sketching a long rectangle and then extruding it into a solid bar. I then added a center hole in the beam so that it could connect to the pivot point and rotate properly. Next, I modeled the seats and handles on both sides of the seesaw using simple sketches and extrusions. I made sure the dimensions on both ends were symmetrical so the design would stay balanced. After creating the main parts, I applied fillets to smooth the sharp edges and then gave the model a cleaner and more realistic appearance. Finally, I assembled all the components together using mates such as concentric and coincident mates to properly align the beam and pivot connection, which would allow the seesaw to realistically move around the center support. Overall, this project improved my understanding of how mechanical parts fit together and helped me develop stronger SolidWorks modeling and assembly skills.
For the assembly stage of our project, my role was to take every individual part created by my group members and bring them together into one fully functioning playground model. This step required careful alignment, consistent mate selection, and a strong understanding of how each component interacted with the others. To ensure the structure came together accurately, I applied a total of 36 coincident mates, 4 concentric mates, 2 lock mates, and 4 tangent mates. Each mate played a specific role in controlling movement, constraining geometry, and guaranteeing that every part fit exactly where it belonged. As I assembled the structure, I made sure that every platform, slide, tunnel, roof piece, and support feature connected exactly as intended. Using this combination of mates allowed me to verify that all dimensions, clearances, and reference points were consistent along the entire group's work. It also revealed how each part contributed to the overall design and how small adjustments in one component affected the rest of the assembly. The assembly processes also helped us identify areas that needed improvement, such as stability, spacing, and safety. By viewing the playground as a complete system rather than isolated parts, I was able to make informed decisions about additional features, including the safety barrier I later designed. Overall, the assembly phase transformed our individual contributions into a cohesive, realistic playground model and demonstrated how collaborative design comes together in SolidWorks. For this slide, I want to explain our overall design approach and how we kept everything consistent across the group. Since we didn't create separate 2D engineering drawings, we designed the entire playground directly in SolidWorks using a dimension-based CAD approach. One of the most important parts of this process was establishing accurate, shared dimensions from the very beginning. I actually started by taking an online playground model and adding all the key dimensions to it: height, width, platform levels, slide lengths, and spacing between features. These dimensions became the reference for the entire group. Everyone used the same measurements to model their individual parts, which meant all components were built to the same scale and would fit together correctly in the final assembly. I also want to add that we used the units MKS in AutoCAD. This step was huge for communication. Instead of everyone guessing or interpreting the size differently, we all worked from one unified dimension set. It made collaboration smoother, reduced errors, and ensured that we brought all the parts together. Everything aligned exactly the way it was supposed to. Overall, this approach helped us maintain accuracy, consistency, and teamwork throughout the project. Throughout this project, the true sparkle of our work came from the complexity of the design and the collaboration required to bring every component together into one cohesive playground assembly. My group and I each contributed unique parts, but the real achievement was seeing how those parts interacted, aligned, and supported one another once assembled. The precision required in mating features, adjusting clearances, and ensuring structural consistency highlighted how much engineering depends on teamwork and communication. If I had more time, I would have pushed the platform design even further. I originally envisioned a more intricate structure with additional contours and interactive elements, but balancing this project with studying for exams and preparing for finals meant I had to prioritize accuracy and functionality over added complexity. Given those constraints, this represents the strongest and most focused work I could produce, and I'm proud of the final result. Overall, this project was a valuable learning experience that strengthened my technical skills, my problem-solving abilities, and my confidence in using SolidWorks to bring a complex idea to life.